Like I said before, section 1.1 is just readings from the book that you'll do, so we don't really need to discuss those here. And so we'll go right into section 1.2. Now, chapter 1 is about geometry. My guess is that in chapter 1, you're going to see some things that are familiar for you and comfortable, and you will almost certainly see some things that are new that are pretty challenging. There's some content in chapter 1 that is pretty challenging. That's okay. I'm going to help you to get to a place where you can master it. We are starting out talking about quadrilaterals in section 1.2. Before we get there, though, there's a handful of things I want to do just sort of as a review. If these things are really comfortable for you and you're like, really, we're talking about this? That's okay. That's okay. Think of it as, oh, good. I already know this. That's great. But sometimes a little refresher is good. It may be a long time since you've taken a math class, and some things might just be rusty. So we're going to do a little bit of review before we start talking quadrilaterals. First thing we're going to review is place value. When we have a decimal point, we have these numbers, we have place value. If you have any questions as we go through anything, please don't hesitate to ask them. You can type it in the chat. You can raise your hand, you can turn on your microphone. Any or all of those are great ways to ask questions. We've got our decimal point there right in the middle of this number, and in the 7, that's the ones place. To the left of that where the 1 is, that's the tens place. To the left of that where the 3 is, that's the hundreds place. And to the left of that where the 4 is, this is the thousands place. This is probably pretty comfortable for most of you, and that's okay. We're just sort of going through a little bit of review here to make sure we're all on the same page. Where place value is going to become really important for us is when we talk about rounding. And it's these place value positions to the right of the decimal point where rounding is going to come into play. Where that 2 is, that's the tenths place. So if we were going to round a number to the nearest tenth, we're going to stop after 1 place past the decimal. That's what rounding to the nearest tenth is telling us to do. Where the 6 is the hundredths place. If we were supposed to round a number to the nearest hundredth, we're going to stop after 2 places past the decimal point. This one makes sense. There's 100 cents in a dollar. And so when we see the price of something is $3.99, what we're looking at there is 2 places past the decimal. That's 99 cents out of what would be 100 would make it a whole nother dollar. So 2 places past the decimal is the hundreds place. And then finally, 3 places past the decimal, something we won't use much, but we need to be aware of it. That's the thousandths place. And so there's our place value positions. Ones, tens, hundreds, and thousands, certainly important. Really important for us when we talk about rounding are going to be the ones to the right of the decimal point, the tenths, the hundredths, and the thousands. Let me know if you have any questions on that. Next up, we're going to look at rounding. So we're given a number. Round 32.184 to the nearest tenth. So here's the process that we're going to go through to round. Please don't overthink this. Don't make it more complicated than it is. We're going to round 32.184 to the nearest tenth. Now, you don't have to write all this down every time. I'm going to be a little more explicit here than you probably need to be. We're going to round to the nearest tenth. So that means 1 place past the decimal. So if I were to round this down, then I'm going to be at 32.1. If I'm going to round it up, I'm going to be at 32.2. And the reason I know that is I look at this number and I see it and I go, okay, I'm going to round to the nearest tenth, which means I'm going to stop right here. And so rounding it down is really just getting rid of all this. 32.1, rounding it up means I got to bump it up, which would be 32.2. Those are the only 2 possible answers to this question. Nothing else is even on the table. It's either 32.1 or 32.2, that's it. With that in mind, now let's look at the process we're going to go through for rounding. So what we're going to do to go through the process for rounding is this, and I'm going to get rid of those two answers so that they're out of our way. I'm supposed to round to the nearest tenth. So I'm going to go on here and I am going to find the tenths place. And the tenths place has that 1 in it right there. That's the tenths place. That's where I want to round to. What I'm going to do is I'm going to look one space to the right of that position. If the number one space to the right is 5 or larger, we round up. If the number one space to the right of the 10th place is 4 or lower, we round down. And that's it. That's the process. So I look at this and I go, okay, I got to find the 10th place. I look one space to the right. There's an 8 in that position. That is 5 or larger, so I need to round this up to 32.2. Many of you, most of you, might be extremely familiar and comfortable with that process. If you're not, please don't take it for granted. This is one of those things where we're going to see problems that eventually become pretty complex, and there's a lot of work to do. And we go through all this stuff when we get to the very end and we round incorrectly and get it marked wrong. I don't want that to happen to you. Now, rounding is a skill that we're talking about. It's an important part of our class. If you do everything right but round incorrectly, then unfortunately your answer's incorrect because we're talking about how to round. That's part of the class. So I want you to be able to round correctly. If you have trouble with this, I don't mind if you ask questions, whether it's in class, by email. But the process of rounding is really right here. If you want to think big picture, originally we said there are only two possibilities here. It's either 32.1 or 32.2. Really what we're doing when we round is we're saying, which of these is the number I was given closer to? Which one's it closer to? Well, it's 32.184. Well, 32.18, that's darn near 32.2. That's the one it's closer to. So that's what we round it to. So if you're sort of a big picture thinker, that's what we're doing, is we're saying which one is it closer to? If you're more of a sort of step-by-step mechanical person, I'd be one of those. Then we're doing this over here. I'm going to find the 10th place. I'm going to look one space to the right. 5 or larger, round up. 4 or lower, round down. That's it. And rounding down would just mean getting rid of everything to the right of that number. Let's look at one more here. 32.184 to the nearest hundredth. So now we're supposed to round to the nearest hundredth. I know my process is right here. I'm going to find the hundredths place. That's where the 8 is. I'm going to look one space to the right. If the number in that position is 5 or larger, I round up. If it's 4 or lower, I round down. Well, it's a 4. It's 4 or lower. I'm going to round down, which means I just drop this and end up with 32.18. I was rounding to the hundredth, so I'm going to keep 2 places past the decimal, and I end up with 32.18. Let me know if you have any questions on that before I let you try one. And we haven't done any polling yet. You'll see what that is on our next page. Awesome. Let's do it. So what I want you to do is I want you to round 14.117 to the nearest 10th. And this is one of the coolest features in Big Blue Button, I think. It's a chance for me to poll you. You'll see exactly what I mean in just a minute. You should see a window pop up on your screen with 3 different possible answers here. Round 14.117 to the nearest 10th, I want you to do it and then answer it. I love these polls. I think they're fantastic. There's so many positives to these. One thing they do is, look, it's great for you to be sitting there listening and taking notes and asking questions when you have them. That's a really good thing. But sometimes you need to be engaged at a little bit higher level than that. And so I get a chance to ask you to do something that engages you at a little higher level where, all right, well, here, now do it. We can be in a classroom and I put one on the board and I say, okay, everybody practice it, and you get to practice it. This is better than a classroom though, because in the classroom, I wouldn't get to see how many people got it right and how many people were struggling. Here, when you respond to the polls, when you take part in the polls, what happens there then is a couple of different things. Number one, you get to see, am I comfortable with this? Am I doing it correctly? If you are, then you can feel pretty good about, okay, cool, got this. If not, then you might need to ask a question. Or maybe when you see the explanation, you're like, oh yeah, now I understand the mistake that I made. But it kind of gives you a different level of where am I? And perhaps just as important as that is it gives me a sense of where the class is. If I do a poll and 2/3 of the people get it wrong, then I need to go back and talk about this some more. If I do a poll and almost everybody gets it right, then I feel really good about where we are as a class. Not every individual, but as a class. Generally, the way that I'll do the polls is I will say, let's take another 15 or 20 seconds, and then we'll talk about it. That's generally my process because I don't want to be waiting around forever for everyone to finish the poll, because sometimes somebody may not be comfortable enough to do it yet. I hope that's not the case. I want everybody to answer all of them. There's no stakes here. There's no penalty for getting it wrong or prize for getting it right. But if I kind of give you a heads up, is we're going to take 15 more seconds, then you know that we're almost done working on this. You can say, hey, can I have a little more time? Absolutely. We can back up and give you a little more time to finish. But that's generally going to be my process. And so then what we would do here is we would take a look at our results of this. And some of you may have been in remote classes where you've done this before. And so I'm saying all this to somebody who already knows. But then I publish it. And we can see there that 12 people had the same answer and one person had a different one. Now, we don't know what the right answer is yet, but generally, when almost everybody has the same answer, chances are that's our correct answer. And let's take a look at this one. So I'm rounding 14.117 to the nearest 10. I need to find the tenths place. That's where that first one is. I look one space to the right. The number in that position is 4 or lower, so I'm going to round this down to 14.1. Since there was a 1 in that position, I round it down to 14.1. Almost everybody got it correct. I feel pretty good about where we are as a class. If anybody has questions they want to ask, you're welcome to do that. But I don't get why it's 14.1. I thought it would be 14.12. Well, 14.12 is to the hundredths place, so it can't be that one. And, we can absolutely talk about it if you want to. Let's try one more. Round 14.117 to the nearest hundredth. I'll make a poll for this. Sometimes it takes me longer to type the poll than it does for you to answer the question. Well, that's okay. Just hang in there with me. So round 14.117, this time to the nearest hundredth. And so we'll go another 15 seconds on this, and then we'll talk about it. So let's see where we are. Okay, not unanimous, but very close to unanimous. What I tend to find is that most of the time we end up with not unanimous, but really close to unanimous. And so as we take a look at this one, 14.117 to the nearest hundredth. So find that hundredths place, that's where that second one is. We look one space to the right. Since the number there is 5 or bigger, we'll round this up. And so that becomes 14.12. Again, let me know if you have questions. That's rounding. Rounding is going to be really important for us all semester long. If you have trouble with it, I want to help you get that fixed as soon as possible. Another review type topic is order of operations. And order of operations, you may remember it as please excuse my dear Aunt Sally. That's how it was taught to me. That's how I've always remembered it. What this tells us is if I have several different mathematical operations to perform, what order do they go in? What comes first? And that P, anybody know what the P stands for? You can type it in the chat over there. What's that P stand for? And if a half a dozen of you type it, that's just fine. I don't mind. It's kind of like one of those things, if we were in a classroom and I said, what's the P stand for? And 7 people raise their hands, then I get a sense of a whole lot of people know. Same thing happens here. Just because somebody might type it in faster than you, it doesn't matter. Thanks, Kevin, Arian, Erica. Yes, it's parentheses. That's perfect. And then more people might type it, and that's great too. It also gives me a little bit of a chance to see your names come across there, which is always good for me. If I mention your name and I pronounce it incorrectly, you just let me know, and we'll get that corrected. I want to make sure I say your name the right way all semester long. But you're exactly right. The P is for parentheses. And we don't have to do this with everyone. The E is for exponents. The M is for multiplication. The D is for division. A is addition. And S is subtraction. And this is our order of operations. If we have all these things in a problem, this is the order we do them in. Please excuse my dear Aunt Sally is a wonderful way to remember this. The please excuse my dear Aunt Sally. It does have one little flaw in it, though. Please excuse my dear Aunt Sally is a great way to remember it, but in this order of operations, it's kind of like a hierarchy where parentheses are at the top and exponents are next, and then multiplication and division here, those are actually equals in this hierarchy. Remembering it as my dear is great to remember that those go next, but multiplication and division are equals in this hierarchy, and we do those at the same time from left to right. What that means is if we had something like 16 divided by 3 times 5. Yes, it's please excuse my dear Aunt Sally. And you might think, well, multiplication goes before division then. That's not the case. Multiplication and division are equals in this hierarchy. We do those left to right. So here we would divide first and then multiply after. I should have made that 16 divided by 4. What's the matter with me? Let's make that 16 divided by 4 times 5. So in that one, we would do it left to right. 16 divided by 4 would be 4 times 5. Then we would multiply to get to 20. Multiplication and division are equals in this hierarchy. We do them left to right. Same thing is true for addition and subtraction. Addition and subtraction are equals in this hierarchy. So we do those from left to right. That is, if we have 22 minus 3 plus 8. Yes, it's please excuse my dear Aunt Sally. You might think addition goes before subtraction, so we do this first, but that's not the case. Those two things are equals in this hierarchy, so we do them left to right. So we're going to do the subtraction first and have 19 plus 8 and end up with 27. Any questions or comments about order of operations? There are going to be problems that come up from time to time where we see different order of operations play a role in the problem we're working on. And I just want to make sure you're comfortable with that hierarchy and the order they go in. All right, outstanding. Now let's talk geometry. Finally, geometry. Common polygons. You are probably familiar with a lot of the polygons in this list. I just want you to be aware that there are certain polygons. A polygon is a multi-sided figure. There are certain polygons, and they have names that go with them. A triangle has 3 sides. It could look like that. That's just a sample triangle. Not all triangles look like that one. A quadrilateral has 4 sides. Could look like this, could be a square. A pentagon has 5 sides. A hexagon has 6. Octagon 8. Nonagon 9. Decagon 10. That's a word we don't hear very often. And then once you go beyond 10, we kind of lose our creativity a little bit. We are math people after all. Like if you had a shape with 14 sides on it, we just call it a 14gon. We kind of lose the creativity once you get to a certain point. Also, it'd be hard to memorize them all if they all had a different name. But basically, I want you to be familiar with these. And honestly, what's most important for us in this class are going to be the triangles. And then our topic for today, quadrilaterals. Quadrilaterals are going to be these 4-sided figures. The triangles and quadrilaterals will be most important for us in the class. The quadrilaterals are what we're going to talk about today. You let me know whenever you have questions. So here's some different quadrilaterals and their properties. These definitions are extremely important. They're specific, they're detailed, and they're really important. And so as we look at these, we want to keep these definitions in mind. We start out with the fact that they're all quadrilaterals, meaning they all have 4 sides. You can look at all those pictures and see that every one of them has 4 sides. Now, there's different things about them. The one at the top is called a trapezoid. And what's true with a trapezoid is it has exactly 1 pair of opposite sides that are parallel. Parallel means they never intersect. And we look at this figure and I can see top and bottom. Those are opposite sides that are parallel. If I looked at the left and the right, and I extend those on forever because that's what lines do, those are not parallel. So what this trapezoid has is it has exactly 1 pair of opposite sides are parallel. In this particular trapezoid, that happens to be the top and bottom. But 1 pair of opposite sides is parallel. We move down to the parallelogram that's next. Oops. Parallelogram has a great name because the parallelogram, both pairs of opposite sides are parallel. So in that parallelogram, the top and the bottom are parallel. The left and the right are parallel. So both pairs of opposite sides are parallel. That's what makes a parallelogram. Moving down the list, now we get to shapes that you're probably much more familiar with, the rectangle. All angles have to be 90 degrees. So when we look at a rectangle, all the angles in there have to be 90 degrees. It's a 4-sided figure. It's a quadrilateral. And then we have a right angle here, a right angle here, a right angle here, and a right angle here. All 4 are right angles, meaning they measure 90 degrees. That's what makes it a rectangle. Again, the definitions are extremely important. Up next, we have the rhombus. Rhombuses come up from time to time. We don't really discuss those as much as like rectangles and squares, but every once in a while they come up. And what's true about a rhombus is all sides have an equal length. So in the rectangle, all the angles were the same. In a rhombus, all the sides are the same. The way that we can mark that is by putting a little tick mark on there to show that they're all the same. If we wanted to show that sides weren't the same, like in our rectangle, for example, we could say that these get a 1 because they're the same as each other, and these get a 2 because they're the same as each other. That's a way we can identify sides that are the same length as each other. is with the number of tick marks, like that. In a rhombus, all sides are equal in length. So all four sides have equal length. That's what makes it a rhombus. Then we get to the square, probably familiar with the square. Square has a couple of specific things. All sides are equal and all angles measure 90 degrees. The word "and" is a really important word. It means that has to happen also. So you have to have all four sides equal in length and all angles are 90 degrees. That's what makes it a square. So those are the definitions of these quadrilaterals, and that's all well and good. We're going to talk a lot about these quadrilaterals, but one thing that's going to come up is these definitions and the relationships between them lend themselves to some excellent true-false questions. And here's what I mean by that. You let me know if you need me to slow down or you have questions. So relationships between quadrilaterals make for really good true-false questions. Sometimes we kind of think, yeah, it's a true-false question. How hard could it possibly be? Well, when we get into these geometry definitions, some of them can be kind of complicated. So let's take a look here. This first question says, all rectangles are parallelograms. We have to decide whether or not that is true or false. Here's the thing. The way I want you to approach this is, let's see if we can show that it's false. And all we need for that is one counterexample. We only need one. If I were to say to you, it's sunny all the time in Las Vegas, that's a sentence you could get away with in casual conversation, right? It's always sunny in Las Vegas, but always is a specific word. If I wanted to prove that statement false, all I need to do is point to one day when it's raining and it's always sunny in Las Vegas. Nope, that's false, because on December 3rd, it was raining. So that's it. It's a false statement. To say something's false mathematically, we just need one counterexample. So this statement here, all rectangles are parallelograms. If I want to, what I want to do is I want to see if I can prove that false. I want to see if I can find a counterexample. All rectangles are parallelograms. All right, well, let's see if I could draw a rectangle that's not a parallelogram. If I can, I've shown this to be false. So, okay, let's try to draw one. So I'm going to draw a rectangle. And let's see here. Okay, so that's a rectangle. Now let's see. Is it a parallelogram? Well, top and bottom are parallel, left and right are parallel. Yeah, that one's a parallelogram. All right, let me try a different rectangle. Let me draw a tall, skinny rectangle this way. Well, you know what? Top and bottom are parallel, left and right are parallel. You know what? Every rectangle I draw is going to be a parallelogram. I'm never going to find a counterexample. That statement is true. Now, I didn't prove it. You might remember if you took high school geometry where you did these two-column proofs where you had like your statement over here and your justification over here. We're not going to do anything like that. We're not going to prove that this is true. We're just going to sort of try to prove it false, and in so doing, convince ourselves that, okay, this one's true. Or we might find out that it's false. Let's look at the bottom. All rhombuses are squares. So let's see. What I'm going to try to do is I'm going to try to find me a counterexample. I'm going to try to draw a rhombus that's not a square. All rhombuses are squares. So if I draw a rhombus, all four sides are equal in length. Well, that's not a square. It doesn't have right angles. All rhombuses are squares. Right here's my counterexample. So that is false. If I can find one counterexample, I can say that it's false. Not as easy as a lot of true-false questions are. I think they're outstanding. Let's have you try a true-false question. Oh, two, actually. So, every trapezoid is a parallelogram is the first question. And then the second one is, all squares are rhombuses. I'm going to set up a poll for this and give you a chance to respond. And so since you have two questions there, there's two responses in the poll. The first answer is for the question at the top of the page, and the second answer is for the question at the bottom of the page. So if you think they're both true, you'd pick true, true. Hopefully that makes sense. Go ahead and think about these for a minute. Your approach is try to find a counterexample. If you can, then it's false. If you can't, you haven't really proven that it's true, but you might be able to convince yourself that it's true. We don't have to be in a hurry on this. I don't think it's necessarily easy to answer questions like this. You may not have really seen very many questions like this before. But give it a try. True or false? Every trapezoid is a parallelogram. True or false? All squares are rhombuses. Let's go another 15 seconds on this one, and then we'll talk about it together. Okay, let's see. Okay, we have strong agreement on this one. Not completely strong agreement, but pretty strong. So let's go and talk about these a little bit. So the first one, every trapezoid is a parallelogram. So what I want to do here is I'm trying to find that counterexample. I'm going to try to draw a trapezoid that is not a parallelogram. Well, let's see. If I draw a trapezoid, that means I have exactly two sides parallel. So here, my top and bottom are parallel, my left and right are not. Okay, so I've drawn a trapezoid. Hey, that's not a parallelogram because parallelogram has top and bottom parallel and left and right parallel. That example right there is not a parallelogram. And so every trapezoid is a parallelogram must be false because here's one that's not. In fact, no trapezoid is ever going to be a parallelogram because a trapezoid has exactly two parallel sides and a parallelogram has both pairs of sides are parallel. I do think that's kind of a tough one, especially if the definition of trapezoid and parallelogram are new for you. The bottom one, almost everybody said true on that. So that's good. All squares are rhombuses. So I'm going to try to draw a square that's not a rhombus. So there's a square. All four sides are equal. So that's a rhombus. Okay, well, what if I draw a really big square? Well, all four sides have to be equal. For it to be a square, all four sides have to be equal. So yeah, every square I draw is going to be a rhombus. So that's true. I can't draw a square that's not a rhombus. It has to be. And so the relationships set up great true-false questions. If you're solid on the definitions, that really helps a lot. Let me know if you have questions on those before we move on to another topic related to these quadrilaterals. All right. Perimeter and area. First, we'll sort of define those, and then we're going to look at perimeter and area of some different shapes. Perimeter is the distance around a figure. So imagine if we have a rectangle, and we're standing here in this corner, and we're going to walk all the way around it. How far did we walk? That's the perimeter. It's the distance around a figure. The way that you can think about this is essentially think of it like if we were making a fence. That's the perimeter of a figure. For perimeter, sometimes we'll have a formula. Every time you can always just add up the four sides. So sometimes we'll have a formula, but most of the time you just add up the sides to get the perimeter. If you think about what we're talking about when we're walking around this figure, we're talking about a distance that can be measured in a straight line. Now, he's making a couple of turns, but it's a straight line distance. How far did you walk? So perimeter is going to have units that are like inches or feet or centimeters or kilometers. It's just a straight line distance with units like that. When we talk about area, instead of thinking about the straight line distance, now it's how much surface does a figure cover? So if we're talking about our rectangle again, it's how much area does this cover? How much space does it cover up? Instead of thinking of a fence, I want you to think of the carpet. If you were going to buy carpet, it would cover the floor. And so when we're talking about area, we're going to talk about units that are square units. If you've ever bought carpet, you know that that's the case. When you buy carpet, you buy it in, well, probably not in square inches, but square feet or square yards, or it could be square centimeters. And the reason that it's squared is because in our first example up here with the guy walking around with a fence, he's just doing a straight line distance. You could straighten that out and make it a straight line. Now, when we look at this, we have this direction and we have this direction. Because we have two directions, we have two dimensions that we're looking in, that's why we have square units. Units won't be a huge focus for me, but I do want you to be aware that if we're talking about perimeter, we're just talking inches, feet, centimeters, kilometers, miles, yards, whatever. If we're talking about area, it's square units, square feet, square yards, square kilometers, whatever they are, because we have two dimensions now. With perimeter, sometimes we'll have a formula, but usually we'll just add up all the sides. With area, though, for area, you're going to see formulas for that. Any questions before we start looking at some shapes? Awesome. Perimeter and area, we're going to start with the rectangle. Now, perimeter we kind of talked about. That's going to be add up all four sides. And we could do a formula for that. With a rectangle, it's typical for us to call this the length and it's the width. And so if I wanted the perimeter of this rectangle, well, I could say I have length plus width plus another length plus another width. So I could do length plus width plus length plus width. And then I could combine like terms here. I have length 2 times, so I have 2 times the length. I have width 2 times plus 2 times the width. So if I wanted a formula for the perimeter of a rectangle, it would be 2 times the length plus 2 times the width. So there's a formula for the area of a rectangle. Keep in mind, you could always just add up the 4 sides if you prefer not to use the formula. But there's a formula if you want to use it. Now, if we were to give some dimensions to this, so let's say this down here is 3 feet, and this over here is 2 feet. And I section that off. So I've got, so there's my 1, 2, 3 feet long, and we cut it this way, and I have my 1, 2 feet wide, right? So I've got my dimensions there, 3 feet by 2 feet. And each one of those is 1 foot by 1 foot. If I look at it, I've got 1 foot by 1 foot right here, 1 foot by 1 foot, 1 foot by 1 foot. How many square feet do I end up with in this rectangle? If each one of those boxes is a square foot, how many are there in my rectangle? So my rectangle here is 3 feet by 2 feet. And what I've done is I have decided to chop it up into little 1 foot squares inside of it. So I've got my rectangle that's 3 feet by 2 feet. So we've said that the length is 3 feet and the width is 2 feet. And I'm going to chop it up. So it's 3 feet and it's 2 feet. So what I've done is I've made it so that I have a 1 foot by 1 foot square, another 1 foot by 1 foot square, another 1 foot by 1 foot square, and then I have them up here too. How many 1 foot by 1 foot squares do I have inside my rectangle? Perfect. Thanks, Jessica. Ashley, I have 6. So there's 1, 2, 3, 4, 5, 6 square feet. So the area of this rectangle is 6 square feet. Now, that works fine when it's 3 by 2, but what happens if my rectangle is 12 by 18? I definitely don't want to chop it up into smaller pieces. What's a shortcut that I can do if I know the length and I know the width that will give me the area of a rectangle? Knowing what we know now. I had 3 feet and 2 feet, and it gave me 6 feet. What's a shortcut that's going to take 3 feet and 2 feet and give me 6 feet? What can I do? What's the process? What's the mathematical operation that's going to get me from 3 feet and 2 feet gives me 6 feet? Excellent, Kevin. That's it exactly. And that's going to be our formula for the area of a rectangle is length multiplied by width. Length times width is going to give me the area of a rectangle. So our formula for the perimeter is 2L plus 2W. Our formula for the area is length times width. Let's try them. So here's a rectangle. It's 13 by 7. So the length is 13, the width is 7. What I want to know is what is the perimeter and what is the area? I'm going to set up a poll for you. To tell me the perimeter and area of that rectangle. So find the perimeter and the area of that rectangle, and you can answer in that poll. We'll go another 30 seconds, and then we'll talk about this one. Let's take a look and see where we are. Okay, pretty good agreement. We're definitely on the 91 for the area, but a little bit of disagreement on the perimeter. So let's take a look. So if we want the perimeter and area of this rectangle. Now keep in mind it's a rectangle, so however long this is the same length, and however long this one's the same length. So if our length is 13, that's true for top and bottom. If our width is 7, that's true for left and right. If I want the perimeter here, I can do this two different ways. I could say the perimeter is 2 times the length plus 2 times the width. And then if I want to simplify that, I have to remember order of operations. Please excuse my dear Aunt Sally. And that means, let's see, if I look at this, I've got multiplication and I have addition. Well, when I remember, please excuse my dear Aunt Sally, multiplication comes before addition. So I'm going to do the multiplying first and add afterwards. And so when we do our multiplying, we'll have 2 times 13 is 26. 2 times 7 is 14. And then finally, we'll add 26 and 14 makes 40. So our perimeter of this rectangle is 40. We don't know what the units are. Inches, feet, centimeters, I don't know. I wasn't given units, so it's just 40. Another way to get the perimeter here, which is perfectly fine, is to say, well, I'm going to imagine myself standing right here and walking around. And that's 13 plus 7 plus 13 plus 7. And then 13 plus 7 would be 20. 13 plus 7 would be 20 more. Add those together. Sure enough, I have 40 as a perimeter. Then for the area, we're just going to use the formula to find the area. The area is length times width. So here that's 13 times 7. We can use an X for times. We can use a dot for times. Either one's okay. We'll multiply those together and get 91. Let me know if you have any questions about anything that we did there. We do have a couple more shapes that we're going to take a look at as far as finding perimeter and area is concerned. But before we go forward, I want to give you a chance to ask any questions you have about those. Okay, very good. Let's talk parallelograms. So for perimeter of a parallelogram, it's exactly what you would think it would be. We're just going to add up all 4 sides. We don't really need a formula for that. We're just going to add the 4 sides. And we do want to figure out a formula for the area. It's not going to be length times width here because it's a little different than a rectangle. But one thing I want you to notice, and some of you who are very visual will see this a lot easier than people who aren't as visual. I tend to not be that visual, so it's a little tough for me, but I'll do my best for you here in making this as obvious as possible. I've got this parallelogram. If I were to chop this off, so I take my scissors out and I cut this triangle off right here. And I'm going to pick that triangle up and I'm going to move it. I'm going to pick that triangle up and I'm going to put it right here. So I'm just taking this triangle and I'm moving it over there. And so now I have this new shape that is right here. And so this parallelogram has some similarities with a rectangle because I can chop off that triangle and make it into a rectangle. The thing is, when I look at the rectangle that I just created, so if I were to chop that triangle off, move it over, and I make this, I make this rectangle over here, right? Well, the length down here is the same, but now the vertical part, that's not one of the sides of my original parallelogram. Just to sort of illustrate that a little bit better, where the rectangle ended up was here, and this was the same. The problem is that piece is not a part of my parallelogram. So what I have to do when I want the area of a parallelogram is I'm going to call this thing down here the base, and the vertical distance from top to bottom, we're going to call the height. It's not one of the sides of the figure, but it's important for me because if I want the area of this parallelogram, I'm going to do base times height. That's going to be the area of my parallelogram. Essentially, it's the idea of I can see a rectangle in here, but in order to get the area of that, I need that vertical distance from bottom to top, which is the height. For perimeter, we're just going to add up the sides. Let's have you try one. So, perimeter and area of this parallelogram. We have all the information we need given to us. Keep in mind that the bottom and the top are going to have the same length. The side on the right and the side on the left are going to have the same length. With that in mind, I want you to find the perimeter and area of this parallelogram. So perimeter and area of this parallelogram. And keep in mind, for perimeter, we're adding up the sides if I were to walk around the figure. For area, we're using the formula. We'll go another 30 seconds on this and then talk about it. And you can let me know if you need a little more time. All right, let's take a look. Okay, strong agreement, not unanimous. Not everybody was in on this one, so maybe we'd be a little careful as we go through it. So the first thing that we'll do is, since we know we have a parallelogram, however long this side is, this side's the same length, so that's going to be 10. Same thing's true. If this is 4, then this is going to be 4. So when we go to find our perimeter, we imagine ourselves standing here at the corner and walking all the way around the external part of the figure. A little bit dangerous here. There's a 3 on the screen, but I'm not going to use it in the perimeter because it's not a part of the outside of the figure. When we do perimeter, we're only doing the outside of the figure. And so that's going to be 10 plus 4 plus 10 plus 4. So the perimeter of this one is going to be 10 plus 4 plus 10 plus 4. We are not going to use that 3 in the perimeter because it's not a part of the outside of the figure. It's on the inside, and that's not a part of the perimeter. And we add these up. Let's see, that's, 14 and 14. So our perimeter is going to be 28. Let me know if you have any questions as we go through it. Now we need the area. Well, the area is just a formula. The area of a perimeter is base times height. The base is down here at the bottom. The height is the vertical distance from the bottom to the top. That's where that 3 comes into play. And so for our area, it's the base, which is 10, multiplied by the height, which is 3. So the area is 30. And again, we weren't given units, so we don't know if this is yards or feet or centimeters or whatever it might be. Any questions on that before we look at one more shape? Okay. Oh, wait. Hold on a second. All right, one more shape. We'll take a look. Trapezoids. We're going to do perimeter and area of a trapezoid. You can kind of see that there's something going on here with that diagonal that's kind of like the parallelogram. And similar to the parallelogram, the height is going to be really important for us. The thing is, we can't really do base times height in this one because the base down here at the bottom and then this piece up here at the top, they're not the same as each other. So we're gonna use those together to find our area. The one at the bottom in this particular picture, the longer base, we're gonna call a capital B. That's our longer base. And then even though it's at the top, so it's a little bit weird to call it a base, but the shorter base, we're going to use a lowercase b. The bases are our parallel sides. So in a trapezoid, we have exactly one pair of parallel sides. Those are our bases. One of them's longer than the other. The longer is capital B, the shorter is lowercase b, and we also have the height. The height's going to be really important for us. When we go to find the area of a trapezoid, what we're going to do is we can't just say base times height, and we can't just say base times height. Those are no good because those would give us an inaccurate area. What we're going to do is we're going to say, okay, I have this base on the bottom and I have this base on the top. What if I took the average of those? That would be the right across the middle. And that's actually how we're going to find the area of a trapezoid. So we're going to say that the area is, we're going to take the little base and add it to the big base and divide by 2. Essentially, we're finding the average of the length of the bases. And then that is going to get multiplied by the height. It's the most complicated formula we've had, but it's really not that difficult. We're just taking the 2 bases, add them together, and then divide by 2, and then multiply that by the height to get the area of the trapezoid. Perimeter of a trapezoid, we find the same way for the other shapes. Just add up all the sides that are around the figure. Remember, you imagine yourself walking all the way around it, add those up, and that's how you get the perimeter. All right, let's have you try one more. The perimeter and area of that trapezoid. We'll go another 20 seconds and then talk through this one. All right, let's see where we are. Ah, really strong agreement on this one. That's good news. All right, let's take a look at it. So first, we'll find the perimeter of this trapezoid. And remember, perimeter is, imagine we're standing on a corner and we walk all the way around the outside of the shape. So that's going to be 6 plus 10 plus 12 plus 10. We're not going to use the 9 because that's not a part of the exterior of the figure. So when I go to find the perimeter of this one, we're just going to add up the exterior sides, which was 6 plus 10 plus 12 plus 10. Now let's see, 6 and 10, that's 16 plus 12 plus 10. 16 and 12 would be 28 plus 10 is 38. So our perimeter here is 38. Again, we don't know what the units are. Could be feet, inches, centimeters, yards. I don't know. 38. Then we need to find the area. And for the area of a trapezoid, we're going to use this formula. It's the little base plus the big base divided by 2 multiplied by the height. And so to find the area here, we're going to have, let's see, the little base is 6 plus the big base is 12 over 2 multiplied by the height. We haven't used this yet, but that's what that 9's for. The height is 9. And so for our area here, let's see, we have 6 plus 12, that'll be 18 over 2 that we're going to multiply by 9. I ran myself out of room down there. That 18 divided by 2 will be a 9. And so that'll be 9 times 9, and we'll end up with an area of 81.